the workshop. Today in the afternoon there will be the handing of the prize for the best PhD thesis in Latin America in classical gravity. So I was just noticing this morning that in only 2 days and a half of workshop, we managed to cover cosmology, gravitational waves, ultramassive black holes, and exoplanets, which are basically 4 of the 5 last Nobel Prizes in physics. So if you are interested for the youngest among you, if you are wanting to pick a line of research, I mean, you have basically the best line of research represented here. And this morning, I'm very happy to have José from the Federal University of Rio Grande do Norte in Natal, so another Brazilian excellence here, talking about the search for exoplanets with a specific technique he will tell us about. Please.
Thank you, Ricardo. Well, it's a pleasure to be here, of course. I was in the FT when I was a student, I mean, many years ago in the Paulista, so that is new for me, but I mean, some faces are the same. No, Rogério. So today, I come back with discussion with Ricardo. We started discussion in Cambridge a few years ago when Ricardo was in the LIGO community. We tried to discuss this connection between stellar evolution and big problems in cosmology. So that makes sense because now I have many nice observations. So one of these observations is this photometry that we did that for thousands, millions of stars at the same time. So I put here some, let's say, some fundamental stuff about exoplanets, but my focus will be microlensing, exoplanets for microlensing. So this is new, it's exotic at the same time, and I think you will figure out that microlensing is probably the best way to know the connection between star and planets. So we have one, we can see one solar system, but when you compare this solar system with other solar systems around the galaxy, we can see that the architecture, the structure of this solar system is not usual. It's really hard. You have no answer for that. So talking about the solar system, I like to start it with this plot, with this very, very easy high school plot. Oh, sorry, the laser point, just to, is this one right?
Yeah, the pointer is the top one.
Okay, thank you. So when you look at the solar system, our solar system, we have small planets in the left. The Earth is here, of course, and we have these 2 big planets in the center of solar system. You have another big ones, these kind of big balls from gas and with some helium and hydrogen. So it's really strange that the big planets in the solar system fit inside the middle range of the solar system. So without other example, we accepted that, but it's not easy to figure out from the theoretical point of view. So that is one of the questions that's coming from this problem is the stellar, how stellar burning, how planet is formed, how connected is star with the planet. So it's not an easy thing when you figure out that it's a turbulent way to do things. Magnetic fields is there. We have all the connection between small process, large scale, time. So that is one of the complications, but the physics is really, really close to explain what things drive our solar system. Here's a plot that shows the sun, the Earth position, this asteroid belt, and the Jupiter. So we can see that large particles probably form in dynamical process all the protoplanets that you can see in the solar system, like the proto-Venus, proto-Earth, and Mars. And this part of small particles did form the big planets in the solar system. That is a paper, it's quite classic paper in the field. And this kind of process, it's more or less accepted for the Earth-like planets and the gaseous, the Jupiter-like planets. From the observational side, we have this very nice ALMA image that is from VHA tau. It's a Orion region object. So you can see the star, you can see the disks, you can see some gaps in the disk that are the position where the planet were formed. So you have no matter because the matter is in the planet. So that is really exciting kind of image. And the simulation of this stuff was did before. So that is one of these cases that the observation meet the observation. I mean, the theory meet the observation, and the observation comes after the theory. So grosso modo, I mean, in large sense, we can see that the process from A to E is a kind of time. When the time passes through, we have the formation of the solar system. And in these small planets and the big planets, and is more or less divided by this fixed line. That is the snow line or ice line. That is the division between planets that are too hot and planets that are too cold. So this ice line is important because life depends on water. And in some sense, water is kind of fundamental liquid to start life. In comparing what this paper from Science Advances show is that these small planets is completely adapted to our solar system view. You have these small planets, and the small planets are here. We have the ice line, and you have the big planets. And this ice line is important, and I stress here because with microlensing, I discuss exactly about small planet in this zone. That is not easy from the other techniques. So, again, rock planets, the snow line, the gas giants. So, I mean, until 2019, until 1995, that was the big picture. The physics of the star formation was quite good to explain the rock planets, the snow line, these asteroids, like we have some very low asteroids that fits in this position, in these gas giants. And I will pass through slide. I don't need this today. But in 1995, Michel Mayor Didier Queloz published the first exoplanet around a solar-like star. That was 51 Pegasus B, that was around the 51 Peg. 51 Peg B was a Jupiter, a hot Jupiter, hot because it's too close to the star, and a giant Jupiter, kind of 0.6 Jupiter mass, and close to the star, short of the rotational period. If you compare this with our solar system, we have a problem. Because it was good, I mean, it was quite good, the connection between the planet formation theory and our solar system. But now we have another star with a Jupiter planet close to the star. So that was a kind of, I'd say, I mean, Michel Mayor Didier Queloz got the Nobel Prize for several reasons, but that was one of the reasons because the field coming very, very, I mean, hot, exciting. I have two pictures here just to, Ricardo mentioned the Nobel Prize. Here's Michel Mayor, that is my thesis advisor, and that is students that are connected with Geneva in the 90s. And here is Michel Mayor taking this professor title from Natal, from my home university. That it was before the Nobel Prize. That is just funny to see these plots. By the way, forming stars is a hard problem because we have to put now migration. The Michel Mayor Didier Queloz point was Jupiter, as close as the stars, need explanation. One explanation was that probably the planets could be migrate from the far away to close to the star. The second point is that we can need to figure out the influence of the stars, the dynamic interaction, the tides, the disk properties, all this stuff together with stability, magnetic field connected to stability. That is, I mean, theoreticians know that that is not easy when you put these things together. And to test these theories, we can use now the exoplanets. The question is that when you look into the exoplanet, or for these many exoplanets that was discovered, we need to figure out if you can compare the physical process during the star formation with the exoplanet that is seen now. What is the connection between the early time of the formation and the distribution that we can find now? So, and that is one of the problems. For example, we have some planets that figure out that are in some desert. When you put mass along the eccentricity, for example, we have some region that there is no planet. And other regions has too many planets. So figure out this desert is a kind of test to the theory of stellar formation, of the planet formation, sorry. The paucity, I mean, we have no planet giant around low mass stars. That is another problem. How figure out that from the theory? And some planets that are, we call that free floating planets. Planets without stars. Strange, but there are some. So that is just to give you some ideas that it's connected with a statistical view of planets in the galaxy. We need to do some, in some sense, a kind of demographic study of exoplanet. And for this, we cannot study star by star. And again, microlensing is important for that, because you can access thousands of stars at the same time. So, in other words, the proposition is really easy. So, study the diversity of planets, do some histograms, and see how the things are, I mean, in the physics connected with the theory. That is the easy things. To find exoplanets, we have more or less 5 tools only. We have radial velocity, that was the technique used in the Nobel Prize planet. Transit, radial velocity, direct imaging, gravitational microlensing, astrometry. I will pass through this very fast. I don't care about all this stuff. Of course, I will talk about microlensing. But it's nice to see how things are. I mean, radial velocity is very easy. It's just a spectroscopy techniques. When the planet go around the star has just some movements around the center of mass. And that could be, measured by high-resolution spectroscopy. That is the radial velocity techniques. The transit is the technique from the Kepler, the Corot satellite, the TESS now. That is, we can measure the light. I mean, we have a photometry, a very, very good photometry that can detect it when the star passes through the stellar disk. You can measure 2 points and take the orbital period. The other techniques is the direct imaging. That is nice too, because you can take the star, here's the star, we can put something eclipsing the star and take a measure of the planet just close to the star. But that is not easy for a star. I mean, the planet needs to be very, very far from the star to these techniques. There's only 1 or 2 planets are inside these techniques. Astrometry, that is important because Gaia is there. Gaia is the new satellite from ESA, and we can measure the position of stars with a very, very good precision. So if you have this precision for the stars, some star that has some movement is because planet is there. So that is quite new, I can say, techniques, and that is possibly for the future one of the techniques that will give us many, many exoplanets. And finally, the gravitational microlensing. So the gravitational microlensing, it's completely based on general relativity stuff. And we can measure some positions, some stars, and figure out the interference of the mass in the background stars when a secondary star passes through the background stars. So the light of these stars is here, and when these 2 stars are in front of the field of view, we have this magnification. And if the target star has a planet, you have a perturbation on this magnification. I will show a little bit more about that. Just to mention these techniques and my team in Natal, last Friday, we just published 1 exoplanet that was almost completely composed by water. This exoplanet is the connection between 2 techniques, radial velocity and photometry with TESS. So now we can use 2 satellites, so 2 observations, 2 messengers, 2 kind of light to study the same planet. So that is some releases from the last week, just to show you some. Yeah, sure.
How do you know it's mainly covered by water?
Well, that is a very good question. Let's answer because it's an exciting question. When you take the radius of the star and the mass, possibly for planets observed from photometry and spectroscopy, we can solve the mass and the radius. And you can write the state equation, like a state equation for a planet. And you have this diagram that you can put the star in the position that is iron, because if it's too heavy and too small, it's an iron composition. If it's too light and too big, it's a gas, it's kind of liquidy or gas combination. And for the star, the position of the star in this, PV, this is state diagrams give us a water world, kind of mainly composed by water. This is one case because we have many observations from this target. We have photometry, infrared photometry, so we connected all the possibilities that we can do for one planet with the star. By the way, our problem is not only the easy cases. The question is that to find planets like the Earth, around the star like the Sun, we have this kind of problem. The Earth has this size and the Sun this size. When you compare the activity of the Sun, all this, the dynamic of the star, the Sun life, these affected the measurement of the radial velocity. I can do the same study about about the limitation of each techniques in compare with microlensing, but that is not the sense here. I will not do the same kind of connection, but for radial velocity I will do, because the Sun is a magnetic star, and the radial velocity is a measurement from spectroscopy. In spectroscopy, when something moves in the surface of the star, in the atmosphere of the star, the spectroscopy has this movement. So if you want, if the focus, the objective, the goal is to catch up a small planet, you need to figure out all the activity of the star, like magnetic cycles, spots, all these things that change in the stellar atmosphere. By the way, so with this, I can probably give you a point. Microlensing is probably the only measurement that you don't care about the star. You have the question, you have the effect, we have the measurements, and we don't care about the star. So a microlensing exoplanet is a kind of planet orbiting stars. And these stars has a background stars and all the stars that pass between us and the background star. And when this happens, we have this combination between the light of the background stars, the lens for the second stars, and a possible planet or a binary or another object, another third body or a second body that they're forming the image. So that is a very easy thing. And it's based more or less in the relativity. You know that before the general relativity, Einstein writes some hints about the detection of the star behind the sun. And Einstein say, well, I expected a 0.84 arcseconds of the deviation of the star. Here's the cartoon. The lens, the sun is here. So this inclination is more or less 0.845. After Sobral, Roger was there, and Ricardo too. We see that many times. So we have here after the eclipse in Sobral and Island Primes. So you got the true value by using the general relativity. And the effect is possible, and you can measure that. So the point is just looking the star that we call the lens, the South Star from an observatory, we can measure the distance between the true image and the lens, the format image. And the more straight, I lost my mouse here. So if you put this idea, just classical equations, like we can measure the distance between the real image and the secondary image, that is just the deformation from the general relativity, we can find the alpha, I mean the distances between the three images, the secondary images. And we can compute this radius. Of course, it's proportional to the mass, and over the, it's proportional to the mass, and of course depends on the Schwarzschild radius. So just writing this equation to fit in a distance and to put the Schwarzschild radius and the distance below, we can write this equation here that we call the Einstein Angle. That comes from the radius, the Einstein radius. And that is not, this equation, Schwarzschild radius over the distance, is not far from the original equation published in 1936 by Einstein. That is the beta here. So Schwarzschild radius divided by the distance. And Einstein say, of course, there is no hoping of observing this phenomenon directly. Einstein was, well, some people say that probably that was the only time that Einstein was not correct. I'm not completely agree, because we know now that we need to observe 1,000 of stars, probably 10,000, 100, I mean millions of stars to get one microlensing. So if you think about 1936, it's probably a statistical view that there's no hope. And by the way, I will pass through some equation again to show that we can do that for one lens to two lenses for many lenses. That is the same process. Of course, to do that, we need a little bit more of geometry just to write things and figure out how all these lenses is connected. But that is not, I mean, we stay in this very traditional way to do physics. And we have here the lens, the Einstein angle. Each of these rays will produce this magnification. That is a very simple problem. And with this, we can expect this kind of situation. The magnification of a single lens without nothing. I mean, a background star, a secondary star, an eclipse, just magnification. The second case is if planets exist. You have these two kind of corners. I mean, you have these two peaks here. That is a single problem with two planets. We have another thing that is how to verify that is a planet. That is like the field of view is drive between the geometry, because you have the background stars, you have the secondary stars, we are here, but the field of view could not be in the same line. So we have many possibilities that need to be figured out, and we call these possibilities, I mean, that is probably the most difficult thing to do with this stuff. We need to compose all the solutions at the same time. So let's go to a more observational. I have 10 minutes more. That's perfect. So that is one of the cases. I'll go to 2012, 2013, BLG 0371. That is one star that one day started to be magnified. And the people say, oh, let's go observe it. The difference between this point and this point is months. I mean, it's 2 months or 3 months. So we observe it every day. You can see the magnification only because 2 stars is one in front of the other. So that was one of the first time that we compare. I mean, the OGO was a survey. You did the observation, we did the model, you started to figure out how to do these things. I will not talk about caustics, but just to give you this idea that the caustic is very important, because the caustic is here, have a very, very nice caustic here. The deformation of the lens when the light passed through, and if the lens is not perfect, the focus could not be a point, but you have this region of the focus. This is this envelope of the light. You can see the same thing when we study microlenses or lenses. For the exoplanets, for example, we have the caustic associated to the system. I mean, we can figure out the magnification, but you can also talk about the caustics of the stars. And I will not give you, I can discuss this solution after. That is a solution, that's a more general problem, is a generalization of the problem. We have all the solutions. We can write a polynomial solutions that is the same way we do for many problems in physics. And we can now do a model for one star in the background, one star between the star and the observer, the pass-through, and the planet. And here, exactly we expected. A magnification, a secondary peak that is the signature of the planet. This question was studied in some cases. For the synthetic case, we can write the caustic. That is the caustic. Go ahead.
So how come the magnification of the planet is so strong? I mean,
The magnification has, the planet has no magnification because the planet has no light. The magnification is the effect from the light of the star and the second one.
I understand, but so how come is it as strong as the one from the star?
Depend the star.
I'm thinking it depends on the compaction. The planet's compaction is much weaker than that of the star.
Yeah, sure, but the point here is how massive is the star? If the front star is bigger or is dense, the lens is strong, and the magnification is more strong than a more, thin star. So the magnification is only connected to the star mass.
No, that's precisely my question. If I see the second bump.
Okay.
So if the second bump is associated to the planet, how come the second bump is as seemingly comparable to the first bump, which would be the star?
In this simulation, we simulated 2 planets, not only one. So the secondary, because we pass through, you have these 2 bumps, is because the geometry of the system changed. In this system, we have 2 planets. It's just the next slide. That is the system that we try to figure out.
Since we interrupted already. So is it correct to say that the main parameter that tells you what is the height of the magnification is the compactness of the object, m over r of the lens?
Yeah, this is the key. The connection between the 2 masses that give the luminosity, the magnitude of the first and the second. And the planet, how close or how far the planet is, will give the time scale of the observation. For 2 planets, that is hours or 1 week, this bump. And from here to here, you have many weeks or many months. Because, a small planet is just turn around very fast. So here you have a planet, and you have these two surveys connected. That is important to mention because it's the first planet detected. And that is from Ogo. Here's a more delicate process. In this case, you have 1, 2, 3, 4, 5 planets in this event. So you can see the caustic is not easy too, by the way. So that is one good example. It's called classical example of microlensing. I will finish talking about this Earth 2.0 because it's a very small planet, and we observed this along the COVID. We observed this in 2020, 2021. And that is more or less the work of my former student, Leandro Almeida. He is the man behind many of these plots. And for many of these observations is from Leandro, we call TED. And that is the planet. You can figure out that it's an Earth mass planet in the time of COVID. We observed this, and we did the model for the magnification. That is the magnification. You can figure out, we can see here the name of all the observatories that was observing this campaign. And more or less the observational strategy is, in Australia or in China, an astronomer started to see a magnification of the star. He called some friends and CTIO in Brazil and Hawaii. I have a problem. One star has started to be more stronger. Can you observe it? Yes, I have time. So that is the way to do these things. Of course, it's not easy because sometimes we are in the observatory, sometimes not. Here is the Leandro observing in Brazil, in OPD. And for this observation, a very nice result is that when you connected the Q is the reason between the mass of the planet and the mass of the star with the same major axis, we can see that our star is this one. So it's actually the more close star to the sun in terms of mass in orbital period. And here's these tracks are the points that was put in 2016, 2019. So that is a very, very nice result because it was done in the COVID. What robotic observation was not easy as observation, and we did. Here's one big part of the observatory that you use, some in Australia, South Africa, France. EOPD is a very nice observatory to do that because it's a small telescope. You can do that very fast. You can just go there and observe. Let's move a little bit more fast. I don't talk about strategy today.
You have 15 more minutes. You don't have to hurry.
Yeah, I have.
Yeah, you can go on until
okay.
10:50.
Yeah, so it's 50 minutes in the whole presentation. Good.
Yes.
So I come back to strategies just to.
Yeah, take your time.
Okay.
Anyway,
this
I'm
is
sure
good.
there will be a lot of questions. So.
Good. So the strategy to do this kind of observation is not easy because we are only in our house with our family, and at some time we got a mail, just, hey, José, I have a high magnification event that is currently undergoing an anomaly. That is, the nature of the anomaly is currently unknown. The event itself is very bright. Ricardo, you asking, 12. 12 means it's coming to here. The magnification is exactly how the light curve started to be, enhanced. And attached the figure from which Zhang, and he did find the anomaly. So the current data is from our LCO, that is the survey. That is seen by Jennifer, that is my collaborator in CFA in Harvard. So, and we got this email, and sometimes we have time in the observatory, sometimes we are just lost the planet because we have no time. And if the magnification is exactly inside, just coming to this, if the magnification wrapping to solve the planet is in a period that you have no time, we lost the planet. So we need to solve the timing when the planet go around and the second peak is there. So it's easy to imagine that finally with microlensing and the actual way to do that, we lost most of the planets. So it's really hard to get a planet because the strategy is not easy. So now we have this strategy. So that is one of the fields that we use. Here is all the fields separated. And for few of these stars, every year we have this follow-up of these stars. And we can, in fact, put this in observations. And times we have this kind of email or Twitter. People use everything today to join the scientists to go to the observatory. And in this way, I can say that the planet that we discover with microlensing is far away, the more exciting, because are exactly in the ice region, exactly the region that we are looking for. Answer a question as how frequently you have this kind of Earth planet with water. And looking from some exoplanets related by microlensing, here you have the mass of the planet and the same major axis. So that is a plot from 2017. Red for transits, green for radial velocity, pink for emergence, astrometrics, and microlensing is this purple. The Earth symbol is this one. So we can see that by 2017, 3,600 planets was discovered. In the situation of the Earth, 0, no planets. That is not only the planet for microlenses, all the planets discovered until 2017. That is what this plot means. For sure, these points here are big planets in short periods, right? These planets here are small planets with short periods. And the blue here are more or less like the Earth orbital periods, but big ones. That is the hot Jupiter, like the first one from Michel Mayor and Didier Queloz. It's a hot Jupiter. It's a Jupiter close to the star, spinning, in a very, very fast spin around. And finally, if you go to 2021, it's not, it's not a big change of the picture. For sure, we have some more nice planet around the Earth, and all these planets are purple. That's mean microlensing, okay? So looking for microlensing planets, that is the focus in microlensing. We have all these planets from big planets with the same major like the Earth, until these planets that are around. And finally, sorry, yeah, go ahead.
So what's it?
So what's the underlying reason for your selection biases? You don't like small or large semi-major axes. They have no problem in masses, but you do seem to have an issue in the semi-major axis.
We have the same plots with many axes. We can do that with masses in same issues or masses with the H. The issues you talk about, it's not. I don't see why this is a problem.
No, I'm not saying it's a problem. So, but you mentioned, oh, look, none of the techniques seems to be homing in on the Earth. But of course, all of the techniques have their own selection biases.
Yeah.
So are these
Exactly.
methods intrinsically having some particular bias that would prevent us from seeing an Earth mass? And then why do I care if I don't see an Earth mass?
Do you remember I mentioned the magnetism of the sun? That is one of the bias. The noise from the star is one of the bias that keep the radial velocity limited by some bias. So that is wow, that I don't hesitate to come back because your question is really important to be not mentioned like that. That is mass again, and the publication data. So 1995, the first one, 50 unpack. And radial velocity started to take many planets. And here's the threshold of 1 Earth mass. So we can see that the bias exists. So it would be not possible with this technique to come into the Earth mass planet. Of course, some groups say, no, we have these extreme stability instruments that can go beyond this level of noise, but it's not easy because the noise is not from the instrument, the noise is from the star. So we cannot, so that is one of the limitations that we can talk about. And by the way, the instrument that we used in this publication that I mentioned was a SPIRO. SPIRO is a spectropolarimeter in the infrared. So we can go with the infrared around this line because with the infrared, the stars seem to be more quiet. And that is one reason that to use infrared is not visible to go beyond this threshold. By the way, let's come back to our, okay. So, yeah, microlensing give us these planets. In 2001, well, not bad. If you compare 2017 from 2021, the comparison between these two periods is because my student did the thesis exactly in this range. So that was exactly the defense slides showing these two. But yeah, I can summarize in terms of mass over some major axis. All the stars that we know, by 2021. The star that we discover, I mean, the planet that we participate in the discovery, that was this very, very close to the Earth mass. And in the background, all this one is also associated to our theme. So that are new exoplanets with the UFRN, the Universidade Federal do Rio Grande do Norte, connected to the paper. And, well, that is more or less in terms of, let's say, publicity or selling something. I can give you the idea that microlensing is really, really an important technique to go far in this field. And we have many issues from the theoretical point of view. I can discuss this in the questions.
Can I ask you something?
Yeah, sure.
Why it's favoring one astronomical unit as the distance, typical distance
So
where you
that-
find of the planet when you find microlensing? It looks like it's centered in one
Remember,
astronomical unit. Yeah.
remember there's no line. The ice line
Uh-huh.
is this line. It's more or less this line. I mean, here is probably too hot. Left side for you is too hot, right side is too cold. That is more or less connected. There's no line. I mean, the Earth is here, so there's no line. Is a little bit not
But
far
then
away
you
from
could
here.
have icy giants or something.
So yeah, so that
cold
is
giants.
why this line is for us is a kind of important line. Okay.
If I can follow up on this, not naively, I would expect the planets detected via microlensing to follow on a line of constant slope. I mean, basically increasing mass and increasing radius.
That is
with
true.
Fixed mass over radius.
That is true.
But no, they seems to be vertical.
I mean, you talk about this envelope here, right? It's not. It's
I
not.
was expected to follow around this line rather than vertical.
Yeah. Well, yeah. The bias that you ask about. One of the bias of the microlensing is the time that we can follow up the event. So we cannot follow up for 6 months. So we have some constraint in this semi-major axis too. Okay. So just putting in a time, it's important probably talk about this 989 because one astrophysicist from Harvard, from CFA, and in the 18th, another one in the 18th from US, published some strange exoplanets around pulsar and around other objects that was not accepted by the community as a real planet. So now we know that in 1989, we have this pulsar planet. In 2019, in the 90s too, we have another planet that was activity, was not real a planet. And that was a scientist from the CFA. And we have, in 1995, the natural occurrence, I mean the natural frequency of the planets from all the techniques, and the situation is, today is more or less here. I did this plot just before taking the flight in the Sunday. Okay, that is just an updated situation, these two. I mean, you can, now you have the eyes to look at for all parts of this plot. Again, you have more or less from here, the ice line, and you have these 2 hot and here 2 cool planets. Okay, Ricardo, you talk about the aspect of these plots. I can give you another idea is that, for example, Kepler is a nice machine to discover planet. It's only associated with these volts 2 hot. And we need an instrument to do same thing like Kepler in the right side of this plot. The instrument is accepted, more or less, is the double first, or the Nancy Roman Space Telescope. That is probably the next big instrument to do that, because it's a really wide field camera. So that is the field of the double first, or Nancy Roman. That is the Hubble field. It's a kid game with this kind of machine because we have millions of stars at the same time, the photometry of all this stuff in the real time, okay? So we need computation for that, and we know that. That is why my student and myself, we started to figure out how to be more efficient, I mean, more focused in the search for solution. That was one of the paper from the Leandro thesis, and it was a process to search more, how to say, focused on solution. That was published in an astronomical journal, and it's kind of Python simulation. We search for all the solutions, and in this search for, we can search planets that are too far, too close, too big, and you can see here, I mean, each peak of that is one possibility in the geometry of the planet, the background in the, sorry, the star in the background, the second star in the planet. So we did this paper exactly to the next WFIRST and Euclid's mission, because that is the kind of science that we think will be relevant, will be strong in the next years, I mean, the next decades, probably. So I will come in from my last slide. So that is, again, that is the same paper, just to be more focused on how to search this region of interest in the simulation. And, well, I would like to give you some range here. Microlensing is important. That is one thing that, my message is that. And probably we can access small planets and the ice line. That is one important thing to say here. It's more sensitive. That is true. We can go to planets far away in the galaxy. We can go to the planets in all the galaxies too. So that is awesome. And the only method also that we can, I mean, connected many things at the same time for the density of planets, for the statistics, I mean, for looking for how common one planet or another one is in the galaxy. It's capable of detecting with some probability multiple planets. That is possible too. Also, in summary, microlensing can be used to study the statistical abundance of the exoplanets in our galaxy. And we can do the science. That was what I expected in my first slide. So I finish say that microlensing can do that. So thank you. Questions, please.
Thank you very much. I enjoyed a lot of your talk. My question is a little bit in like the one that Luis asked. So you mentioned that the fact that it's measurable is the magnification, right? That gravitational potential from the planets effect on the path of light, right? But I don't think I understand very well how you need to model the caustics in order to take into account this effect. Because, I mean, wouldn't that just be a question of let's wait for the potential to, the gravitational potential on the plane that you're observing, the potential of the planet being added to the star one, and then you just have a single magnification event? Why do you have to model the caustics in order to take into account this magnification? I don't think I understand it very well.
Yeah, probably the best way to answer your question is think about the simulation. How simulated this? We started to putting together a background of photons, okay? That is photons that's coming from the background star. Second point, we take a secondary element, secondary mass, you pass through this background of photons. When the first light passes through the potential, we have one lens. When the second ray passes through, we have the second element of the lens. I mean, we call that second lens because it's connected to main lens. So the time goes through, and you have this combination, and the image is coming in this different way. So that is one star in the background and one star in the front, okay? Let's do the second simulation. Same one, but you put a secondary component, a planet or a binary, a broad dwarf, whatever. We have the first, the star coming, the first light coming too. We have the caustic, we have the formation of the star mass they form in the light, but the planet has a dynamic timing that is different from the timing of the star coming through. So all these things is connected with the magnification. So that is, magnification could be really more complex than one peak or two peaks. It could be negative, it could be really in a big...
Yeah, because it's not something that's just a point being added to the potential,
Yeah,
right?
yeah, but my point now is, once simulated all these phases, you can change the place where you are to look at this event. This could be completely aligned, this could be like that, this could be, you know. So the image format is the combination between the background, the star, and the observer. So in the simulation, we can play with this. In the acoustic, it's one kind of, how can you say, manner to see the same thing. Not the same thing, but you know, it's associated acoustic, like in a glass. When the sun coming, the acoustic we change at the same time. So the acoustic is the final combination between everything in this phenomenon.
Okay.
Yeah.
Thank you.
So it's a very naive question. So you have the lensing effect on the background star. So the question is, do you see the star that's in the front, or just see the magnification of the star in the back?
Yeah, we have just the magnification is between the background star. You have the magnitude is constant. You have no magnification. The star alone is there. One day, this star started to be magnified. And we can, if you search it for something, you can see the second star that coming close.
So you can see the second star.
You can see the second star.
Okay.
And you can, well, depends of the star. Some
Right.
star is not possible, of course.
Right.
But yeah, in some sense, we can see, you can help search the star if you figure out which star is hard. It's not frequently,
Yes.
but it's probably a nice thing to do. I don't know if we did that for one star precisely, but we know that one star coming, and we can observe the secondary star, the two stars at the same time, and probably follow up a little bit more the secondary one.
Yeah,
Depends of the brightness.
Yeah. So the reason I ask is because this microlensing technique was also used to search for dark matter in terms of the macroscopic dark matter. So if you don't see the star, you don't know if it's a star. So it could be interesting.
Yeah, I discussed with Thais before my talk that I guess that the guys from dark matter was the root case of this exoplanet, because all these guys looking for something wrapping in these stars, and he figured out, wow, probably a planet is possible, and that was a little bit, the way was corrected to do planets. So the same of W first. We talk about galaxies. Nobody talk about microlenses from exoplanet. A student from Natal is trying to figure out how possible will be W first for microlenses. We don't know, because it's a really wide camera, but yeah, who knows?
Okay, thank you for the nice presentation. I have a curious question about the planet which has water. What are your thoughts? Can it support life?
Sorry, could you?
Can the planet which has water, the one that you observed, a curious question, can it support life? I don't know.
Yeah, absolutely. The main point is life. Well, people discuss a lot about life now. So if life is possible in one planet, in another planet, I personally say that life is possible in many places in the universe. The moons, it's probably a good place to life be there. But planets in this ice zone, it's the main target to search for life. And the other NASA missions, like now WFIRST, for example, is we try to do this transmission spectroscopy. It's, in some senses, it's close to this process. We have one star, and the planet is around this star. And when the planet go through, we can take the photon, can observe the photon that go through the atmosphere and know if the atmosphere has some water. CO2 was discovered 2 weeks ago, I guess, in one exoplanet. That was exactly the techniques that could be relevant to search for life. And if the planet has water, it's more nice because life needs water to start it. Big proteins, you know, big chains. That is one thing important to life.
You have a question?
So yeah, so this is also a very naive question, following Rogerio's. So everything here you're doing in the optical. So can you do microlensing with our frequency? In particular, I'm thinking, given what you mentioned, all the structure and activity of the sun that mess up with your noise level.
Yeah.
So if I now look for a coherent source of radiation, say I'm thinking pulsar on the radius, of course I have to be lucky for something to go through, but we have been following pulsars for decades through nanograph and the PTA. Is there a chance to do it with radio?
Yeah, well, that is not a naive question, my friend. It's infrared. I mean, it's not easy for me to know how to adapt the lens in the optical to the infrared. My naive answer is yes. I think the lens, all the physics will be the same. Is we just change some lambda to the left. We will try to see, lens in the near infrared or in the red. And things like pulsar, it's not easy to observe it, what's going on close. But yeah, I think with the next NASA observatory, I guess, is Louvois, you'll be observatory in 3 channels: visible light, red, and UV at the same time. So probably with this kind of machine, we can start to figure out, you know, what's happening in the visual light at the same time in the red, in the blue. But I don't know. I don't know about the lenses in the other lights. Yeah, frankly.
There are no further questions. I have one question, so I take advantage of my question. Sorry, you're putting the ice belt around 1 astronomical unit, but that's assuming that the star is sun-like. I mean, isn't there more variation of stars?
Yes, that is one part of the problem. Of course, like, assuming that the star like the sun, could have planets like the Earth, we search for this combination of the star. But that is an assumption to start with something. Okay. And but it's like you found a friend, a brother that you lost. We started looking by people that is close to you, right? So that is the same process. So yeah, this
working assumption.
Yeah, is one assumption. But of course, the moons probably could be a good. Moons close the star. It's probably one good place to be there.
Okay, one last call for question. If not, let's thank José.